I'm Annie from E&I Department, Satyabama Institute of Science and Technology, deemed to be University, Chennai. This session is on generating Hamming codes. In general, a group of binary bit in digital data is called a binary code. There are many kinds of binary codes which will fall under one of the following category. It could be weighted codes, non-weighted, sequential, reflective, alphanumeric, or error detecting and correcting codes. Hamming codes fall under error detection and correction codes. When we say error detection first, what could be a possible error in digital data? Let's consider passing digital data from a transmitter to a receiver end. Say I'm passing a data of 1001 from the transmitter over to the receiver end. The person who receives it at the receiver end may not be sure of the data integrity due to the possible interference of noise into the data. As shown here, the second bit has flipped from a 0 to a 1. This could be a probable error. So the very first requirement would be to detect the occurrence of an error. There are codes which just does the work of detecting if there is an error occurred during the transmission or not. Parity check is one such example where we have additional bits added which would say if there is an error occurred or not. The advancement from the detection would be correcting the errors apart from detecting it. Hamming code is a classic example of correcting errors also. Hamming code was devised by an American mathematician, Richard Hamming. Parity bits are added along with the data. They are basically intervened with the data rather than being added at the ends of the data signal. And the code which is generated by the addition of data and parity together is called as a Hamming code. We'll consider an example where we are to generate a Hamming code for the data 1101 using odd parity. We will have to break down the solution into steps. The very first step would be we'll have to find out the number of parity bits required, which basically depends on the length of the data. Once the number is identified, the next step to do would be to position the parity bit in between the data. Once the data parity bits are positioned, we'll have to assign values based on following odd or even parity. The solution would be to generate a Hamming code with data and parity written together. Step 1, computing the parity, would be to find out the value of p, where p stands for the number of parity bits, x stands for the length of data or the number of data bits. This expression shows us 2 raised to p is greater than or equal to p plus x plus 1, where x is a known value and p is the unknown value which we are going to find out. Let's consider the same example 1101. So from here, x value is equal to 4, which is basically the length of the data. Now p is found out with trial and error basis. We'll have to substitute values for p and find out if the expression is satisfied or not. I'll start with p is equal to 2. When p is equal to 2, my expression is not satisfied, so I'll have to increase the value of p and try out p is equal to 3. When I do so, I find that the expression is satisfied. So I found out in step 1 that the length of parity, the number of parity required, is going to be 3 for our example. Now I know the length, next I need to fix the position of the parity. The parity will take positions like 2 to the power of 0, 1, 2, 3 and so on. Since we have only 3 parity positions, it's going to be P1, P2 and P4. And the structure of the Hamming code will look like this, where you have the data and the parity bits intervened. The position of parity bits are fixed. The next task in hand is to identify the unknown parity bits, for which we have a table designed. You have the format of the data and parity put together. The suffixes are the bit locations, which are the decimal equivalent of D7, D6, D5 and so on. The decimal equivalents are expressed in its equivalent binary values starting from 1 to the 7th position. This table would be the same for any of the Hamming code that we are to generate. The only change would be the length of the table might increase. I mean, the number of columns would increase if we have a longer data. We'll start with the very first parity bit P1, and we'll have to keep in mind that we are doing it for odd parity. When I start for P1, I'm basically required to look at the data D3, D5 and D7 bits. Why D3, D5 and D7 is because P1, the 1 position lies in the first bit position, which is LSB first bit. D3, D5 and D7 all have 1s in the very first position, which is LSB first position. So I'm going to count out D3, D5 and D7. The value of D3 is 1, D5 is 0 and D7 is also 1. Counting the number of ones, I have two number of ones. I am required to maintain odd parity, which means only if I give P1 is equal to 1, I will maintain the integrity of odd parity. So I am going to assign P1 is equal to 1. Moving on to P2, I will have to look at the second bit position of 1. So P2 requires to look at the data bits D3, D6 and D7. The value of D3, D6 and D7 all seems to be 1 here, which means the count of 3 odd numbers already. So I am required to give the parity bit P2 as a 0 in order to maintain odd parity. The last parity bit in our example is P4. I am required to look at the third bit position of 1, which is the MSB in our case. P4 requires D6 and D7 to be looked at. Both are 1, which means the number of 1 counts is an even number 2. I need to transfer it over to an odd number. So I am required to make the P4 bit as 1 in order to maintain odd integrity. With the values of P1, P2 and P4 introduced now, we have Hamming code which is generated. Data and parity together is 1101 101. So that will be the Hamming code for the given data of 1101. Hope this session on generating Hamming code would have been useful. The next lecture would be on checking the error in Hamming code.